Okay, let's dive into something that might feel a little, well, a little tricky to grasp.
Hmm.
The fourth spatial dimension.
Mm-hmm.
We get height, width, depth. That's our everyday world, pretty straightforward.
Right, it's what we experience constantly.
But the idea of another direction, totally separate from those three, it's a bit of a head-scratcher, isn't it?
Yeah.
Our brains just seem built for three.
That's really the heart of the problem. As, three-dimensional beings, our intuition about space just stops there. To even start thinking about a fourth spatial dimension, we have to really stretch conceptually.
Totally.
Yeah.
So for this deep dive, we're going to try and do that stretch. We're going into this pretty mind-bending territory.
Sounds good.
And our main guide for this is going to be the brilliant Carl Sagan. Back in 1980, on Cosmos, he explained this stuff with his unique clarity. You could almost call him the scientific Mr. Rogers,
Yeah.
making complex stuff feel understandable.
He absolutely had that gift, a real knack for finding analogies that made these huge, abstract scientific ideas feel, well, relatable and engaging, especially for visualizing things you just can't see.
He really did. And just to get another perspective, we're also looking at a more recent take, a YouTube video by a high school student explaining it.
Oh, interesting.
Yeah, and what I liked there was the use of different comparisons, like stacking folders, and connecting it to mathematical patterns. It just shows how this concept keeps sparking new ways to think about it.
That's great. A fresh perspective is always valuable. Different generations might connect with different analogies, and it shows this ongoing effort to make these, frankly, abstract ideas more accessible.
So our mission here is to take these different insights from Sagan, from the student, and really try to, wrap our minds around this fourth spatial dimension.
Right.
We're hoping you get those little aha moments, those clicks of understanding, without us just throwing dense mathematics at you.
Exactly. We want to offer a clear, hopefully intriguing way into this area of science. Sort of a shortcut to appreciating some pretty profound ideas about how the universe might be put together.
Okay, so let's start with Sagan's classic approach, the analogy. He asked us to imagine a two-dimensional world, flatland.
Ah, yes, flatland.
Right, to help us get how creatures in a simpler dimension might perceive something from a higher one. So picture a world that's just length and width, like a totally flat sheet of paper. And the beings there. No concept of up or down.
In that reality, yeah, everything exists on that single plane. The very idea of a third dimension, something existing above or below them, would be completely beyond their understanding, just impossible for them to conceive.
Now imagine a 3D object, like an apple, passing through this flatland. What do the flatlanders actually see? They wouldn't see a whole apple, would they?
No, absolutely not. Their perception would be strictly limited to the cross-section, the intersection of the apple with their 2D world.
So like, as the bottom of the apple first touches their plane, maybe they see just a couple of points appear out of nowhere.
Precisely. Maybe a few separate points initially, depending on the apple's shape at the very bottom.
And then, as more of the apple moves through their plane, those points would expand, maybe merge into a bigger shape, maybe even split into weird sections as, like, the core and the outer parts pass through.
Exactly. It would appear as a sequence of changing 2D shapes, growing, morphing, maybe splitting, and then shrinking back down to points before vanishing completely as the apple passes through the other side.
So from their point of view, it's just this bizarre light show of shifting shapes. They never grasp the single, solid, three-dimensional apple causing it all.
Their experience is just fundamentally limited by their dimensional reality. They see a series of what must seem like disconnected two-dimensional events. They can't perceive the unified 3D object behind it.
And this is where Sagan makes the leap. He uses this to shine a light on our own potential blindness to a fourth spatial dimension.
Right.
Just like the Flatlanders couldn't truly get the 3D apple, maybe we as 3D beings are just as limited in picturing something that exists in four spatial dimensions.
It's a powerful analogy because it really forces you to confront the limits of your own perception. If, hypothetically, a 4D object interacted with our 3D world,
We'd only see slices of it.
you'd only perceive its three-dimensional cross-sections, and those might appear to us as strange, maybe objects changing shape or appearing and disappearing in ways that seem to violate our normal understanding of physics.
Which leads us nicely to the tesseract,
Yeah.
the four-dimensional cube.
The hypercube, yeah.
Both Sagan and the student video touched on this, and they both hit the same wall.
Yeah.
We basically can't visualize it directly. It's like, I don't know, trying to imagine a brand new color.
Our spatial intuition is just completely built on three dimensions, X, Y, and Z. We can move forward, back, left, right, up, down. A fourth spatial dimension would mean moving along some new axis, call it W, that's perpendicular to all three of those.
Perpendicular to up, down, A and D, left, right, A, D, forward, back at the same time. My brain just stalls there.
Exactly. It's a direction our bodies and our everyday experience give us absolutely no reference for. It's a completely new way to go.
But, okay, just like we can draw a cube on a 2D piece of paper, it's not a real cube, it's a projection, sort of a shadow.
Right, an imperfect representation.
We can make 3D projections of a tesseract. You often see them drawn as like a cube inside another cube with the corners connected.
Yes, that's a common projection. And it's useful conceptually. It helps illustrate some properties, like how a tesseract has 8 cubic faces, or cells, just like a regular cube has 6 square faces.
Okay, 8 cubes making up its surface.
In a manner of speaking, yes. But that 3D projection, that cube within a cube, it's still just a shadow. It's a flattened glimpse of the real 4D structure. It doesn't give you that intuitive feel for its four-dimensional shape.
And this isn't just like a mathematical curiosity, is it? You mentioned physicists needing this stuff.
Oh, absolutely not just a curiosity. It's crucial for many cutting-edge theories in physics. Think string theory, certain cosmological models.
Right, I've heard string theory needs extra dimensions.
It does. Many theories propose extra spatial dimensions beyond the 3 we see. They might be incredibly small, sort of curled up, or maybe structured in a way we just don't directly interact with.
Hidden from us.
Hidden, exactly. But understanding their mathematical properties, like the geometry of a tesseract, is potentially key to unifying the fundamental forces, like gravity and quantum mechanics, and getting a more complete picture of reality. It helps model how particles might behave in higher dimensional space.
So it loops back to Sagan's apple again. The Flatlanders' weird experience with its shifting shapes gave them clues about the third dimension, even if they couldn't see it.
Precisely.
So maybe our 3D world, our physics, contains subtle hints about a fourth dimension, even if we can't directly, point to it or picture it.
That's the hope. By carefully looking at how dimensions build on each other, mathematically and logically, we can try to infer characteristics of higher dimensions, even if our senses are stuck in 3D.
Okay, let's talk about that stacking idea from the students' video. That felt pretty helpful. They described 2D, like Flatland, as basically stacking up infinite 1D lines next to each other.
Right, like pages in a book making up the book's width.
Yeah, or like their folder analogy.
Right.
And then our 3D world is like stacking infinite 2D planes on top of each other.
It's a good visualization for the progression. Each new dimension adds another independent direction, and you build the higher dimension by assembling infinite copies of the lower one along that new direction.
So following that pattern, a 4D world could be imagined as stacking infinite 3D spaces, like our entire universe, along that mysterious fourth direction.
Logically, yes. Though the student was right to add the caveat, it's not just placing them side by side. The connection is more fundamental.
What do you mean more fundamental?
The key is that each new dimension must be perpendicular at a right angle to all the previous ones. Just like height is perpendicular to both length and width, this fourth spatial dimension would have to be perpendicular to length and width and height simultaneously. That perfect perpendicularity in all directions is what defines the structure.
Okay, got it. And this stacking idea also relates to perception, right? The student pointed out that when we look at a 3D sphere, what we actually see is a 2D circle. Our retinas are 2D surfaces capturing light.
That's a great point about our visual limitation. Yes, our direct visual input is two-dimensional. Our brain does amazing processing to infer the third dimension from clues like shading, perspective, and comparing images from two eyes, but the raw input is 2D.
And they took it further. A 2D being would likely only perceive things in 1D, like seeing only lines as objects pass through their world.
Exactly. If their vision worked like ours, they'd perceive 1D cross-sections. A circle passing through might look like a line segment that grows and then shrinks.
So, okay, here's where it gets really wild, if that holds true. Maybe we aren't truly perceiving our 3D world in its full three-dimensionality either.
It's a mind-bending implication, isn't it?
And a 4D being.
Right.
They would perceive our entire 3D world all at once. Like they could see inside everything, inside me, inside this building.
That's the logical extension, yes. Just as we can look down on a 2D drawing and see its entire interior at once, a 4D being could theoretically perceive the entirety of our 3D space simultaneously. The concept of inside and outside might be very different for them. Privacy would be difficult.
Whoa, okay. The student also laid out the math pattern. 1D line. 4 lines connected make a 2D square. 6 squares connected make a 3D cube.
Right, with faces meeting at right angles.
So theoretically, 8 cubes connected make a 4D tesseract, with 4 lines meeting at every corner point.
That's the structure, mathematically speaking. 8 cubes as the boundaries, meeting in specific ways, with 4 edges converging at each vertex. But again, as both scientists stressed, really visualizing that arrangement, our brains just aren't equipped for it.
Yeah, it feels like trying to understand, I don't know, non-Euclidean geometry back in school. My brain just kept snapping back to flat planes and straight lines.
It's a similar challenge. Our intuition is built on Euclidean 3D space. The math gives us a logical framework to explore beyond that, even if we can't form a perfect mental image. We can understand the properties without seeing it.
Now, we should definitely tackle that common point of confusion, time as the 4th dimension.
Yes, very important distinction.
People often say the 4th dimension and meantime. But in this deep dive, we're focusing purely on a potential 4th spatial dimension, right?
Absolutely crucial. Yes, in Einstein's relativity, time is treated mathematically as a 4th dimension, combining with the 3 spatial ones to form spacetime. But it's fundamentally different from another spatial direction.
How so? What's the main difference?
Well, the most obvious one is you can't move freely back and forth in time like you can in space. Time flows, or at least we perceive it as flowing, in one primary direction.
Right, no easy time travel, unfortunately.
Right. Not as far as we know. And time isn't just another dimension alongside space. It's interwoven with it. It's the dimension in which events happen within space. It exists across all spatial dimensions.
So it's not like space is X, Y, Z and time is just W?
Not in the same way. Time is integrated differently. The student mentioned time dilation, right? Astronauts aging slower at high speeds.
Yeah, briefly.
That's a perfect example of how time behaves differently. Its passage is relative, affected by gravity and velocity in ways spatial distances aren't quite the same. It underscores that time, while dimensional, isn't just another spatial dimension.
Okay, that makes sense. So spatial dimensions and the time dimension are different beasts.
Different beasts, exactly. Both part of reality's fabric, but distinct.
Right. And finally, there was this other really fascinating idea they both mentioned. Curved dimensions.
The geometry of space itself.
The idea that these dimensions might not be perfectly flat and infinite, but could be slightly curved in a higher dimension.
Yes, this comes up in cosmology and advanced geometry. Thinking about the overall shape of the universe. Just like a line drawn on a sphere looks straight locally, but is actually curved in 3D space. Our seemingly flat 3D space could have a very slight large-scale curvature that we wouldn't notice unless we could perceive it from a 4D perspective.
So following the pattern, a 1D line, if it's curved enough in 2D space, becomes a circle.
Correct.
A 2D surface, like a sheet of paper, if it's curved in 3D space, could become the surface of a sphere.
Right, a finite area with no boundary.
So could our entire 3D universe be like the surface of a 4D hypersphere?
Yeah.
Curved back on itself in a 4th spatial dimension.
That is one possibility explored in cosmological models. It would mean the universe is finite in volume but still wouldn't have an edge or boundary, just like the surface of the sphere.
Wow. Okay. Could that curvature, if it exists, tell us anything? Could we measure it somehow as a clue to that 4th dimension?
That's a huge question in cosmology. Scientists look for evidence of large-scale curvature in the cosmic microwave background radiation, for instance. So far, measurements suggest space is very close to flat, but a slight curvature isn't ruled out. Finding definitive curvature would imply something about the larger dimensional structure, potentially.
Which then spirals into that almost sci-fi question. If our 3D world is curved in a 4D space, could that 4D space be curved within a 5D space?
Yeah.
And so on. Does it just keep going?
Infinite nested realities. That's one of those profound unanswered questions that pops out of this line of thinking. Mathematically, you can keep adding dimensions. Whether that reflects physical reality, well, we just don't know. There's no evidence for it currently, but it's a fascinating theoretical possibility.
Okay, wow. Let's try and bring this back down to our 3 dimensions for a moment. Recap.
Good idea.
We started with Sagan's flatland analogy. Super helpful for seeing how our own 3D perception limits us.
Right, understanding limitations by analogy.
Then we tackled the tesseract, the 4D cube, acknowledging we can't truly picture it, but seeing why physicists find studying these higher dimensions so important.
The mathematical structure is key, even without visualization.
We looked at that stacking idea dimensions building on each other, and how our 2D vision might filter our 3D reality.
And how a 4D being would perceive us quite
We
differently.
made sure to separate the idea of a fourth spatial dimension from time.
Crucial distinction, space-time versus extraspatial dimensions.
And finally, we touched on that really mind-bending possibility of curved dimensions. Maybe our whole universe existing as a shape within a higher dimension.
The potential geometry of reality itself.
You know, the thing that really stays with me from all this is just that jolt. Realizing how much our understanding might be fundamentally capped just because we're 3D creatures. It makes you wonder what else we might be completely missing, you know?
It absolutely does. It's humbling, but also amazing that we can even think about these things using logic and math to explore realms beyond our direct senses.
It really is.
Yeah.
So maybe here's a final thought for you, the listener, to chew on. If our 3D reality is just one slice, one perspective, within a larger, higher dimensional existence, what other fundamental parts of reality might we be totally unaware of? Just like those flatlanders had no clue about the apple's true roundness, its upness, could thinking about that possibility change how you see the universe, even just a little bit?
Yeah.